In this video, we're going to learn about applications of the ideal gas law. And the first is molar volume. So if we know that we have 1.00 moles of any gas that are held at STP, which is standard temperature and pressure, or 0 degrees Celsius in 1 atmosphere, we can figure out the volume that the gas occupies using the ideal gas law. Now, if we divide both sides of that by pressure, we get that the volume is equal to nRT over P, and substituting in our 1 mole of gas and our gas constant and our temperature of 273 degrees Kelvin, which is 0 degrees Celsius, and dividing by the pressure of 1 atmosphere, we can find that the volume occupied is 22.4 liters. And that's a constant that works for any gas. That 1 mole of any gas, as long as we're at STP, it will occupy a volume of 22.4 liters. Next, we're going to do some derivations involving molar mass and density, again using the ideal gas law. So we know that molar mass is equal to the mass of a substance divided by the number of moles. If we have a lot of a substance, then we're going to have many grams, a lot of mass, and we'll have maybe many moles, but that ratio is going to be equal to the molar mass. Now, if I rearrange that by multiplying by the number of moles on both sides and dividing by the molar mass, which is that capital M, we get that the number of moles of a substance is equal to the mass of that substance, lowercase m, divided by the molar mass, or capital M, of that substance. And now we have an N that is the same as exists in the ideal gas law. So we can just substitute our little m, or mass of a substance, divided by the big M, the molar mass, in place of the N in the ideal gas law. And there we have it. Rearranging, we can get that the molar mass of a substance is equal to the mass of it times the gas constant times the temperature divided by the product of pressure and volume. From here, if we know the molar mass, we can also find density. Now, density we know of as being equal to mass over volume. And in this equation, this rearrangement of the ideal gas law, we do have a mass over a volume. And so again, we can do a substitution where density is taking the place over mass over volume, the place of mass over volume, and we get that the molar mass of a gas is equal to its density times the gas constant times the temperature divided by the pressure. Rearranging from there, we can get that density is equal to the molar mass times pressure divided by the gas constant times the temperature. So let's solve a problem. We know that there's a nitrogen oxide of some sort. If it's NO, N2O, N2O3, NO2, et cetera, we're going to figure that one out. We have a sample of that gas that weighs 1.211 grams and occupies 677 milliliters. We do know that the temperature in the lab is 23 degrees Celsius, and the air pressure is 0.987 atmospheres. So we can calculate the molar mass of that gas, and from that we can figure out exactly which nitrogen oxide it is. So again, we're going to start with PV equals nRT, and we can rearrange this so that we're solving for N. Because we do know P and V, we do know T, and R is a constant. We don't know the moles of gas, even though we do know the mass of the gas. So we substitute all the variables and constants in, and we find out that we have 0.0275 moles of this nitrogen oxide. From here, we can say that the molar mass of this gas is equal to the mass of it divided by the moles, and we know that we have 1.211 grams of it that we're dividing by the moles that we just figured out, and from there, we can say that the molar mass is equal to 44.0 grams per mole. Now, this is something that we could have figured out based on the previously derived equation of molar mass is equal to mass times RT over PV. I find this easier in the sense that you've done a lot with PV equals nRT. It's one equation, and you can sort of go from our moles using another equation that you're fully aware of, that you've used for a long time, molar mass being the ratio of grams over moles. and you could do it in that two-step process. But if you do want to memorize another equation, this is it. Um, and of course, knowing that we have 44.0 grams per mole as our molar mass, we can realize that that is going to be equal to two 14s and one 16, meaning two nitrogens, each weighing 14 grams per mole, and one oxygen weighing 16 grams per mole. That gets us to our 44.0 grams per mole, and that gives us the formula N2O. All right, so on to density. What is the density of NH3 at 0.913 atmospheres and 20.0 degrees Celsius? Well, if we know that PV equals nRT, and we know that density equals mass over volume, we can take the molar mass of the gas, NH3. We find that it's 17.04 grams per mole, and we can put that in for our mass. Now, this is based on the assumption that we have 1 mole of NH3. But it frankly doesn't matter because the density of ammonia is going to be the same whether you have a little bit or a lot of it. It's an intensive property. So whether we have half a mole, 1 mole, or 10 moles, the density is going to be the same as long as the conditions, the pressure and the temperature are the same. So for simplicity's sake here, I'm just going to say we have a mole of NH3 and we know its mass, right? Now we just need to figure out its volume so that we can plug that in to find the density. Now that volume is something that we can get from PV equals nRT. Rearranging, we get that V equals nRT over P, and substituting in 1 mole, because again, we're assuming a 1 mole sample, and our R, and our T, which is 293 degrees, 293 degrees Kelvin. Sorry about that. And then dividing by our P, we find that our volume is equal to 26.3 liters. And we can just substitute that one in to our D equals M over V. And we find out that our density is equal to 0.648 grams per liter. Now, often you've used milliliters in the past as your volumes because typically solids will have a rather high density. Bear in mind that for gases, we're typically going to have grams per liter as our density. And of course, just as in the previous case, this is something that you could have done with a simplified equation. We know that density equals molar mass times pressure over RT, but rather than memorizing another equation, you also could just use PV equals nRT and D equals M over V to figure out your solution. Anyway, that's all for this video. Hope it's helped. Feel free to leave any questions or comments in the comment section below, and thanks for watching.